All right, class. I am back again after having taken a little break and stuff, and thought that I would put this last in a series of power lectures to bed. It's really power lectures and review of impedance and review of how the perfect inductor, perfect capacitor, perfect resistor reacts. I could go into a deeper understanding of how they react with frequency, but I'm just not going to do that right now because we have too many other things to do. All right, so let's look at our third power lecture, right? And in this lecture, what we really are looking at is we're looking at a capacitor and what the impedance is of the capacitor. And as I've always mentioned, although a capacitor has no resistance whatsoever, a capacitor does have reactants, right? So I'm going to put plus J. A lot of other professors that teach it as 0 minus J 1 over omega C. Or a lot of them say that it's 0 plus 1 over J omega C. And you might think to yourself, oh my God, is 1 over J the same as minus J? Think about it. We'll look at that in just a second anyway. But yes, you can write it in a variety of different ways. I'm going to write it in a couple ways right here. Right, so that's how it's written, or it's written as 0 minus J 1 over omega C, which of course would be the same thing if you think about it. And then some people write it as 0 plus 1 over J omega C, which is the worst way to teach capacitive reactants, just an impedance. It's just the worst way to teach it because it throws everything all out of whack. It's as if the student is supposed to know that 1 over J, let's just look at that for a second. Now we know that 1 is equal to 1 plus J0, right? And we know that J is equal to 0 plus J1, right? So if I've got minus J, or let's say, yeah, whatever, 1 over J, let's do that. So 1 over J equals, I'll just write this out in its phasor form. This would be 1 at an angle of 0 degrees. And J, of course, would be 1 at an angle of 90 degrees. So 1 over J would be 1 at an angle of 0 degrees divided by 1 at an angle of 90 degrees. So what would that be? That'd be 1 divided by 1, which is 1, and then 0 minus 90, which is minus 90, right, which is minus J. So yes, 1 over J also equals minus J. Does everyone see that? And you would have to know that and have understood all complex numbers. And in many ways, you're being taught complex numbers and complex number theory in the class. You get it, of course, with a whole variety of other worthless mathematics stuff that they try to teach you, but it doesn't really mean anything until you see it applied in your technical courses anyway, right? But it certainly helps a lot when you do get to that point in your technical course where you want it proven. So anyway, that's what we've got here. And this is the way that I like to teach the capacitance of that. And the way that you would write that as a phasor is 1 over omega C, right? That's the magnitude. at an angle of minus 90 degrees. And we can use minus 90 degrees here because we're just adding and subtracting angles all the time when we're doing this. We're not doing anything like taking square roots of complex numbers in their phasor form, so don't worry about that. All right, so that's what we've got, and that's the capacitance of thing. And of course, omega, you know, I say omega, you say 2 pi f. And don't forget what that 2 pi stands for. That's for radians per cycle, and the F stands for cycles per second. The cycles cancel out, and you've got radians per second. So that's what we've got. And I think in the last video, I said that we were going to have a frequency. Let me just draw another waveform over here. That we're going to have a frequency of 1,000. Now, let's do that same thing here. So let's say that the frequency of this waveform is 1,000 hertz, which is cycles per second. And 2 pi, of course, times that. We've got the same thing. 2 pi times 1,000 is going to be 6,283. So 6,283 radians per second, right? So knowing that, and then if we were to, draw our circuit, so the circuit that we've got for this, the same circuit as we've got for the other two, just now, of course, I really mean to point out that there would probably be resistance in this circuit too. So it'd be like a capacitor, but there would still be a little resistance in here and everything else. Obviously, you've got a voltage drop as you go around there, so what is actually happening. Now, let's look at, let's not forget what power is, by the way. Power is V RMS times I RMS. So we know what our voltage is going to be. It's going to be the same as always, 10 volts. And we can write that in so many different ways. V of t equals 10 volts peak, of course, times the sine of omega t. And that's because it's a really omega t plus 0, isn't it? Because I don't have anything after it doesn't mean that there isn't a phase shift that could be associated with it. There's not in this case. And in this case, I'm going to try to draw a good sine wave this time. Look at that. That's not too bad. So if I got that right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. Oh my God, I accidentally actually drew it correct. It doesn't look right to me, but I'm sure that it is. Now, and then we've got some type of capacitance too. Let's actually pick some type of capacitor. Let's say a 1 microfarad capacitor, right? Now 1 microfarad, that would be 1 times 10 to the minus 6 farads. And we've got to keep it in farads because, we have to multiply consistent primary unit combinations that we give nicknames to, like a farad, so that we know that when we talk about farads, we're talking about kilogram, meters, seconds, amps, those things, those primary units all put together correctly. So let's just look at that then. So if we had that omega c, let's look at two things. First of all, omega c is going to be 1 times 10 to the minus 6. So this is 6.23 times 10 to the 3, and then it would be 6.26 times 10 to the minus 3. I hope everybody sees that. So 6.283 times 10 to the minus 3, that's omega c. Now what would omega c be? And then what is 1 over omega c, right? Because 1 over omega c we see is an ohm, isn't it? So this would be a mole. I've drawn that upside down, and it's called a mole, but it's really a 1 over ohm. And then if I did 1 over omega c, and of course that's going to be in ohms, you can see the difference between the symbol for a mole and the symbol for an ohm. By the way, in Europe, that's called a Siemens, and that's why we don't call it Siemens here in the country for obvious reasons. We call it a mho, M-H-O, the opposite of ohm. If you're out there and you're working with American engineers and they refer to it as a mho, you'll know what they're referring to. So what is 1 over 6.23283 times 10 to the minus 3? And that is 39.48. 39.48. Well, that can't be right. just a second. Let me do that again. 6.2. My calculator hates me. Okay. Exponent 3. All right. 1 over that is 159.16. I'm sorry, 159.16 ohms. All right, that's 1 over omega c. So we've now got z, and we can actually write z sub c down. Z sub c is going to be, I can write it in several different ways, but 159.16 ohms and an angle of minus 90 degrees, right? I could also say that it was 0 minus 159.16 ohms if I was writing it in the rectilinear, the a plus jb complex number notation, right? So either way. But we're going to be dividing this and stuff or multiplying, so we want to use it in its phasor form. And we've already got V in its phasor form too, 10 volts peak at 0 degrees, right? So we can figure out what I is going to be. So we know that V equals IR. Let's always do that, or V equals IZ in this case. And that means that I is going to equal V over Z. And V, we know, is 10 volts at an angle of 0 degrees. And Z is 159.16 ohms at an angle of minus 90 degrees, right? So I think everybody can see how this is all falling together now. So I get 0.06283. 0.06283 amps. And that would be peak, wouldn't it? Because we're talking about peak voltage right there. So if that I could also write it out as 62.8 milliamps peak, right? Oh, I forgot our angle. So 0 minus a minus 90 degrees. So that would be positive 90 degrees, right? Positive 90 degrees. And we're back to the positive 90 degrees. So where is a positive 90 degrees? You know, if you look back here, and of course I didn't leave myself enough room, but that would be moving this 90 degrees. And of course that'd be 1, 2, 3. And how do I do that? 1, 2, 3. I'm way out here, which is outside of the line that we're supposed to be at. But I am going to do that, and I'm going to do it with red pen here, or actually red is good for, I'll do it with blue. I don't know if you can tell the difference between blue or not, but this would look like this. And you're probably saying, hey, is that leading the current or the voltage? That seems to be leading the voltage, doesn't it? And you're thinking to yourself, well, what does that really mean? It's leading the current now. Let's just write this. This is the current, and this is the voltage. And so you can see now that the current is leading the voltage. So for a capacitive reactance, the current, and remember what I said before, think of this, this is a timeline, remember. The earlier comes before the later, so this is back in 1800, and this is in 1850, right? So that's why this happens before this does. So the current is leading, or it happened before. Think of really when I say leads, as the current happened before 90 degrees. Current leads voltage by 90 degrees. And of course, for an inductor, the voltage leads the current by 90 degrees, right? All right, that's, but let's get back to the power now, right? Remember, power equals VRMS. So let's think of what the power is. The power now for the RMS, it's going to be 7.071 volts. That's the voltage. And that voltage is at 0 degrees. And then what's the current? Well, as you can see right now, we've got the current 62.8 milliamps peak, right? So if I have 62.8 milliamps peak, that means that that's going to be equal to 44.4 milliamps RMS. And of course, it's still at the same angle, 90 degrees. So I've got 44.4, and now, you know, I might as well say times 10 to the minus 3, because that's how I put it into my calculator, ARMS. That's volts RMS, of course. I want to always emphasize that this is always RMS that we're working with for power calculations in AC network theory. All right, so let's just multiply that together. 7.071 times 0.0444 amps, and that gives us 0.3139 watts, right? Or equal to 313.9 milliwatts. And how does that power flow? Does it flow like power flows in sync with the frequency like it does with the resistor? Remember, with the resistor, power flows, now true, it's rectified, so it's always positive, you're always losing power, but every cycle for that power is actually, I think that's 2 cycles too. If you think about it, if you look at that, that might be 2 cycles. It might double the frequency anyway. Anyway, but let's look at this. So what have we got here? We've got the current is positive, and if I was to extend, you know, the voltage back here, we would see that the voltage is negative. But let's just look at these 4 nodes up here. So now I've got a positive current and I've got a positive voltage. So we know that our power is going to look like this. Now here we've got a positive voltage but a negative current. So the second quarter wave, the power goes down like that, right? And then for the third, we've got negative, negative, so it goes back up and it's a power loss for that quarter cycle again. And then here we've got negative, positive, so it becomes a power addition for that last one. And so really, when we look at this, and we've got a perfect capacitive, we never have that, by the way, we never have a perfectly capacitive and a perfectly inductive circuit. That's just not how it works. I'm just showing you the fundamentals of how these things sort of want to shift the current around. And then you can sort of see, well, is this mainly inductive, or is it mainly capacitive, or is it mainly resistive? What is it? Because all of the stuff that we've done so far is to look at the individual components and how they really react with power and everything else. But what I want to go into now is looking at, circuits and starting to use mesh analysis with complex numbers in, a complex circuit, and look at the voltages and the currents in that circuit. So that's where we are. This will be the 4th in a series.